Hello, Miss Jody here. Coming to you with our first video for physical science. Now that we've been separated, I wanted to continue on with some of our work so we could get some things done during this time. And of course, with it being online, we're not going to be able to do as much of the hands-on components of our regular learning. So what I thought we could do is work through some of our notes and some of the lesson material that we have to accomplish during this time while we're separated. And then when we come back together, then we can do the experiments and some of the journal things that we needed to do for the journals. And that way we could still finish the journals for the year, because I don't want to give up on our wonderful journals. This one happens to be Isabella's. And so what I plan to do is to give you a video for what we're working on, and then have you take notes. And so basically my idea was for us to take a half sheet of computer paper and just cut it in half, or whatever kind of paper you have, and just cut it in half, fold it in half and cut it or whatever, and take the notes on that, because then when we come back together, I'm going to keep all the tabs for the notes in the journals as we go along, so that I can leave spots, like say for instance, if this is something, this circuit activity was something that I wanted us to do, and we weren't going to be able to do it separated, but I wanted us to do it when we got back, I would leave a spot for this in the journal. Of course, we were already able to do this, so that's good, but I would leave a spot in the journal for us to do that. And so when we come back, all the little note pages, I'll be keeping the labels, and then all the little note pages that you create, we can just glue in right there underneath the label. And so that way we still have your notes done, and all the learning continues, even though we can't do all the special things we like to do in our hands-on way of learning. So one thing, do note that you can't write on the back of the half sheet, because I'm going to be gluing it in, obviously. And then also what I've been suggesting is to actually write the title on the back. Like if it was this one, electric circuits, you write electric circuits and then do your notes on this front of it. That way it would be easy for me to go through and get them all in the right spot according to what the label is. The label says, okay? And then just keep all those little half sheet notes for me. And like I said, I'll keep this side of it going. And then in the end, we will be able, hopefully, to come back together and do our work together. The other thing is, if there is a diagram, like if you remember this diagram when we were learning about the generation of electricity, when we were on the electricity and magnetism, and the coal generation, and then the nuclear power generating. So if I had a diagram for you, then I would send you that in a PDF over the Google Classroom for you to print out. And I tried to just, so far this week, I've tried to only make one page of a diagram, or one printout sheet which had maybe 2 diagrams on it per class. Our lesson today doesn't actually have any diagrams for the journal, so we don't have to put any in. But if for some reason the lesson did have the diagram, I would send it to you. You could print it out, and then when we're going along in the lesson, you could color it or do what I ask you to do on it, take notes or whatever. So those would already be done also. So we could do our notes, we could do our diagrams, and every now and then if there's something simple, like a really simple craft or something, I could say, or a little activity, then I could say, hey, do this, and keep that with your lesson, and we'll glue it in, okay? So with that being said, I want to get to the lesson that we're working on right now, we were in the middle of, and that is one of the chapters on the forces in creation, the fundamental forces. So we had already started way back, and I'm using Isabella's for this part of it because my notes aren't very good prior to this, because I didn't have to write them out all straight and nice for you. And some of my pages don't even have notes, because sometimes I just write in the book, and because I have taught it for so long. So I'm using Isabella's and reviewing. So after we were done with understanding what electricity and magnetism and all that was, we started, and let me find it, flip through here while we started the topic of, no, actually it was before electricity and magnetism, all the way back before the electromagnetic force. We had the topic of the fundamental forces. somewhere. Course. Let me see. Oh, okay, all the way back to the gravitational force. So we had a little discussion that there was going to be 4 main fundamental forces. Now, these aren't just the forces of like, you know, tension and those are parts of these main 4 forces, but these were the 4 main forces that sort of governed everything and held everything together. So we had the gravitational force, we had the electromagnetic force, we had the weak force, and the strong force. So we had an introduction to it, and then now we've been going along each one of them and spending more time on it. So we talked about the gravitational force and the theories behind that, the electromagnetic force, and that's when we spent a lot of time with understanding electricity, understanding magnetism, understanding them being united by James Clerk Maxwell, and all of that good stuff. So we did gravity, we did electricity and magnetism, and them coming together to create the electromagnetic force as a moving. Now remember, if you call something a force, it's something that can start and stop motion, and it's got power. You know, it's the thing that's doing what we need to have done. And when it comes to the fundamental forces, it's the keeping everything going and acting the way that we have figured it out to act in the world of physics. Okay, so after we did electricity and magnetism, then we moved on to the weak force. And so the weak force, we started first of all with just understanding the structure of the atom, because these last 2 forces, the weak force and the strong force, are forces that only that are acting upon small distances, meaning they are the forces that are part of working with the nuclear world. So they should be called like the weak nuclear force and the strong nuclear force. So you can remember that these 2 forces are in the really, really small side of things. And so in order to understand that, we have to understand the way that the atoms are put together, of the theories behind the atomic world, and understanding the old models, then the newer models, and sort of what we think is going on in this atomic world. So we spend a lot of time explaining how this works with, okay, what's inside the atom, what we think, right? So the electrons flying around, and then inside having the protons and having the neutrons, the positives and the neutrons in the middle. And then we talked about how Niels Bohr, if you remember, he created a model that was kind of flat and helped us be able to see what was happening with the amount of protons in the middle, and then the electrons that were orbiting. Now we know that this is not the model that is an accurate view, because we don't think atoms are flat 2D objects. We think of them as 3D, and so they're a 3D up and at it, kind of flying around, and all of these the electrons are flying around in all of what we call these orbitals now in the quantum mechanical model. And so we understand that this Niels Bohr's model is not accurate for the sense of what it really looks like, but sometimes this helps us understand the structure of an atom, and helping us understand how it fits together with knowing whether an atom is an ion, if it's lost an electron, also if an atom is an isotope, meaning it has more neutrons than what you would normally think it would, and or even why atoms would even want to bond, because the open spaces that are in the energy shells. And so Bohr's model is not accurate for what it looks like, but accurate to help us understand some of these harder things. So we went through and focused on the structure of the atom. Now, with that being said, I had already put the weak force label here because we were going to get into the weak force. But we really spent these 2 pages, some of you, depending on how big you wrote, and then I put in the periodic table that we were using to figure out these models, and I wanted us to practice some more around the outsides here. So, and then we started really talking about what the weak force actually is. So then I decided I'm going to go back and put a label over top of this and put the structure of the atom, just so we understand, or whatever, the anatomy of the atom. I don't know how I'll word it, but basically, so I can save the label and put a new label when we actually start talking about the weak force more in specific, okay? So I will be changing that. But anyway, so we went through, we figured out how you could know how many protons a particular atom has, depending on its place in the periodic table. And these that have been colored on Isabella's, lithium, magnesium, let's see, aluminum, carbon, nitrogen, fluorine and chlorine, and then krypton. Those are the ones we did. So each time we would make a model, and you can see all the models over here. Good job, Isabella, on making these models here. We had to figure out about the how many protons they had, how many neutrons, how many electrons, and then trying to figure out the world of being stable for bonding, having any openings, and that the atoms want to get to that octet rule and try to fill up their shells, and they'd rather either give away electrons if they only have a little in a big high energy shell area. They'd rather give it away and then instead of try to fill it all up with the rest that it needs to become full. And so we talked back and forth about the stability of the atom when it comes to the electrons. Now today when we talk a little bit about the stability of the atom when it comes to radioactive decay, it's going to be a little tiny bit different but similar. So we'll have to look at that with stability. All right, so we focused on all this and we practiced a few of them and I think we got it down. And just as a reminder, when we are talking about the two different sides to the atomic world of being an ion or being an isotope. Okay, so remember the ion is when you have taken on a charge, because either you lost an electron, so now you have a positive charge, or you've taken on some electrons that weren't really yours in the bonding process, and so therefore, or even not in the bonding process, but therefore you have the if you've taken on more electrons and you have a negative charge because you have more than you should. And so we talked about that. That's ionization. So that's being an ion. But then we focused a lot on the isotope. And it's important for us to understand isotopes because isotopes will help us understand this next topic, which is the radioactive decay. And so with the isotope, it was more about how many of the neutrons you have. And so we talked about the isotopes being a little bit different, and I do have to correct this here, Isabella, just so you don't think we're supposed to have our number over here. Carbon 12, carbon 13, carbon 14. And I might have wrote it wrong on the board, which wouldn't be a shocker, but I'm pretty sure we got to keep it over on that side, and that way we are illustrating the isotope world. On this side, when we write in chemistry, I'm just trying to do it better because Isabel has this great handwriting, and then here I just made it all not so great. There we go. When we write on this side, like if I put a number 2 over here or a 2 plus, I'm talking about charges, and that's more of the ion world. So I want to keep it over there, but I'm sure I probably wrote it wrong on the board, and that's probably why you wrote it like that. Okay, so carbon being an isotope means that he has more of the neutral particles inside. I shouldn't say more, but basically there can be different amounts of neutrons within the different types of isotopes. Because even what we would call the regular carbon, carbon 6 on the periodic table, means that he has 6 protons, and that means, and when I look at his mass, and he has 12 in his mass, if you take 12 minus 6, that tells you he's got 12 neutrons. Because remember, the electrons are so minute and so that their mass doesn't even really register on the scale, so we don't need to include that as much in our numbers there. And so if he has a mass of 12, then 6 of those other mass units are going to be neutrons. And so he has 6 neutrons. So the normal, what we would say, oh, that's the normal version of carbon, is really just carbon 12. If he has 1 more neutron, he's carbon 13. 1 more neutron than that, he's carbon, has 8 neutrons altogether, he's carbon 14. And so this would be the isotope world. Now, sometimes these isotopes can get really big, and there's, because they get really big and the nucleus becomes like out of balance, then we also will call that an unstable situation. And we're not talking necessarily about evening out like we were talking before, about evening out the filling up the shells. That's the original, like, not being stable, and atoms wanting to be stable and organizing those electrons, having them even out within the shell, the energy shells that they have, or what we would call now the orbitals that they have. But now, moving into the next one, I'm going to switch from Isabel's book to mine, and we have I'm going to, like I said, put on this new, the weak force tab on this one, and then cover up the old one that said the weak force and put the structure of the atom, something like that. Okay, so this new part of the lesson is now understanding this new force. So we had to understand the structure of the atom, because the weak force and the strong force are going to be forces that govern the atom and the nucleus of the atom. So we have to know how it works, right? So we had to understand the structure of the atom and understand how you become an ion or how you become an isotope. All right, so now with that in mind, we can now move into understanding the weak force. Now, one thing about the book is it does not really go into a lot of the weak force. It just says basically that the weak force is just another aspect of the original one we just finished up, the electromagnetic force, and just another aspect of it. And we see that among many things in physics, that there's a lot of intertying. We used to think magnetism was separate, electricity was separate, and then we're like, oh wait, they're the same. They're just two aspects of the same force, and they're intertwined. You can make a magnetism with electricity and electricity with magnetism. And so this is just the weak force is just still a part of that positive negative kind of pull situation we saw with the electromagnetic force. And it says that it can be referred to as the electroweak force. Now, if it becomes part of this force and it becomes the electroweak force, then really we only have three fundamental forces. We've got the gravitational force, if that's not one day united with all of them, but we got the gravitational force, we got the electromagnetic weak force, and then we'd have the strong force. So really we'd only have three. But the reason scientists and teachers separate it is because it helps you understand. If you separate it a little bit, it helps you understand more specifically in the area of one of the processes that's governed by the weak force, at least partially governed by the weak force, and that's what we call radioactivity. And so in the book, it really doesn't get all in depth about the weak force, because they, oh, you already understand this concept of how this works between the positive and negative charges and the attraction and the repulsion and all that stuff. So now I just want to focus on radioactivity. And so that's kind of cool, because there's a lot to go over anyway, and we can spend enough time just learning about radioactivity. All right, so radioactivity is the process that this weak force is going to be governing. Like I said, only a portion of it. And it's going to be all focused on radioactive isotopes. So when we talk about isotopes, I just talked to you about that. Isotope is when you have more or less of neutrons. You have a different version of yourself, carbon-12, carbon-13, carbon-14, whatever. So that's an isotope. Now, radioactive means an atom with a nucleus that's not stable. Now, we're not talking about necessarily just the stability of, do you have all your spots filled in your shell so that you can bond? That's more a bonding chemical reaction application to learning about the atoms. When we were talking about, if you remember, I don't have it in my book, but the little open spots that I just was showing you with Isabella's book. Let me show you again, but these little open, remember we would draw them out on the board, these little circles saying, okay, this many electrons are in this shell, but he still has some open spots, because each shell can fill a certain amount, 2, 8, 18, and on. Remember that pattern? And so that's more of a chemistry application of it. But when we're talking about the stability of the nucleus, a lot of times with these radioactive isotopes, it's that they're getting so large and you have so many neutrons in there, way more than the normal amount that you would have if you had, say, an even version like carbon 6 protons, 6 neutrons. We're talking about these isotopes that have way more than the amount of the proton of that particular atom. So we're talking about things like uranium-239 and all that, like these big radioactive isotopes. So, and they don't have to be big, as big like that, but they're going to be lower down on the periodic table. Some of these big ones that are going to cause some trouble here. So when an atom has a nucleus that is not stable, the nucleus must decay in order to become stable. So the stability, again, is not about necessarily how many electrons you got flying around in your open spots. It's more about balancing out the energy that's in that nucleus. And so every particle has energy. So the neutrons, you got the protons, you got the electrons, and then of course all the particles that make them up. This is just us talking at the surface of these, but then in particle physics we already know that protons are made of certain things, and then the electrons are made of certain things, we think, and then the neutrons are made of certain things, we think. And so there's just a bunch of stuff going on, a bunch of energy in this little tiny atom that we can't even see, that's jam-packed with energy. And you know how I always say it's like a big fat atom. I say he's fat, meaning he's got so much, he's like bulging over with some of this amount of neutrons or whatever. The farther we get down on the periodic table, the bigger guys. All right, so with this radioactivity, we're going to have 3 main radioactivity categories. And I don't know why the book starts with the beta decay. Most times you teach it's alpha, beta, and gamma decay. And it's kind of good to see it in that order because that also is showing you intensity, like how dangerous some of these things are in the sense of this radioactivity. And so it's better to see as alpha, beta, gamma, but it's okay. I put that at the end so we can visualize that. All right, so beta decay. This is the little symbol for beta decay, and that you'll see when you study radioactivity, radioactive decay. So it's when the nucleus changes one of its neutrons into a proton. It does so by making a neutron emit an electron. Now, this is a weird concept. If you've never studied anything about the particles themselves being made of smaller particles, then you're just like, what? A neutron is turning into a proton? Like, how? He's a proton. You don't think like that's possible, because you've always just learned you got your proton, he has a positive charge, you got your neutron, he's got a neutral charge, and you got your electron, he's got his negative charge. You're just like, well, you can't just change into whatever you want to change into. But the reality is we think that there is a changeability among these these particles because they're made of smaller things, and there's an exchange of particles, as we will see a little bit later. So whenever we're talking about the beta decay, what we're seeing is that this neutron, I'm going to try to draw it out here so it makes a little bit of sense for you, hopefully. So I'm going to take uranium-239, okay? So this being an isotope, that's showing us that it's how many, not necessarily how many neutrons, but its mass, so that I can figure out how many neutrons. So he's uranium-239, that's his mass, and so you can write it this way, 239U. Okay, so I can look at it and I could say, okay, I get on the periodic table and I'm gonna find uranium, and let me see if I can use Isabella since this was already here. Looking pretty awesome. Let's see, uranium. Where's that little doodad? Right there, number 92. So remember, on the periodic table, these two little dots represent these two lines that are pulled out of the periodic table, or otherwise it would be this long, big, this would all be shuffled down. And so he is down here on this side. Okay, so he's number 92. So number 92, and so that means he has 92 protons, and then he has 92 electrons, and that's just, you know, if he's not ionized, he's just an evened out guy, no charge to him. So he can be not charged at all, but still be unstable in his nucleus. And so it's not like a zapping, like positive negative, like we talk about with ionization. It's an instability about the size of his nucleus. So the question would be, how many neutrons does he have? And if you remember, we would take the mass, so like 239 minus 92, that would give me 7. Look at me doing this old-fashioned math here. Oops, no, 3. That I obviously can't even do, and take that to 1, so 147. So he has 147 neutrons. And so if you look at him, you say, okay, he has 92 protons. Don't worry about the electrons, they're flying around. This is just showing that he's not charged. So he's got 92 in the middle, and then he's got another 147 in the middle with him. That's a lot more than this regular amount, okay? So he's got a lot. So too many within that nucleus all jammed in there creates that instability. So what he's going to do is he's going to have to decay. And as he decays, he's trying to get rid of some of that instability within the center, within his nucleus mass. And so what happens is, like this says, that a neutron is going to eject an electron and turn into a proton. And that's when you, again, say, what? I'm sorry, what? Well, if you think of it, a neutron is neutral, right? So that means he has some positive and he has some negative packets of energy or whatever inside him. And so, because he's balanced out. So if he loses this negative part of him and that some of that negative is spit out, he's still got his positive side. So really, what is a particle if he's just positive and he doesn't have the negative? Then he's a proton, really, because protons are just all positively charged, and electrons are all negatively charged, and neutrons are both. So when he ejects this negative, this electron, we call it a beta particle. So he ejects this beta particle, and so therefore all he's left with is just his positive. So that means that in the end he had 92 protons, but really he's going to take on the form of the element above him now, the number 93, because he really has 93 now, because this one becomes like a proton, right? And so in the proton world, if you have 93, you would be Neptunium, which is the next one up above uranium. So in his process of decaying, he became Neptunium, but not just good old-fashioned just Neptunium, but Neptunium isotope. And whenever this decay process takes place, they call this decayed product the daughter product. And so uranium-239 will slowly, and this is a slow process, will slowly decay into Neptunium-239. And so when we look at that, you say, okay, well, he did this decaying thing, and he started out with his mass number, that's how much he weighs, 239, and then Neptunium is 239 too. That's the same mass. But yeah, it is, because he didn't lose anything that was massive. Now remember, when we talk about the way the atom is, the protons have a good amount of mass, the neutrons have a good amount of mass, but the electrons, they're so minute, they don't have much, they're not going to even register on the scale barely. So losing one little negative electron is not going to change your mass, right? And he still had that same situation go on, even though he kind of would have lost a neutron here, he would have still gained one here. So no mass has been lost. So we have this number stays 239 NP. And so the book kind of tells you, so this is that process whenever a beta particle, the neutron changes and the negative is released and he turns into a proton. There's a little bit more to it, and there's really actually a whole lot more to it, but it doesn't want to get into it in your book. But it does say that in this neutron to proton decay here, an electron is emitted